Welcome to The Explainer. I am absolutely thrilled to have you with us today because we are heading straight into the molecular kitchen. If you've ever looked at a chemical formula and wondered how those tiny, invisible atoms actually stick together to form literally everything around us, well, you're in the perfect place. Today, we're looking at chemical bonding not as some abstract mystery, but as a step-by-step recipe. Using a brilliant visual tool called a Lewis diagram, we'll decode the exact rules atoms follow to build molecules. So grab your mental aprons and let's get cooking. Okay, let's dive into our agenda for today. First up, an intro to Lewis diagrams. Second, the ionic bond of sodium chloride. Third, the covalent bond of hydrogen gas. Fourth, the covalent bond of carbon dioxide. And finally, reviewing the bonds. Section 1. Intro to Lewis diagrams, the foundation. Before we can really start cooking up our molecules, we've got to understand our fundamental ingredients. And our absolute starting point for any chemical recipe is valency. Now, valency is basically defined as the number of electrons in the outer shell of an atom that are available to form bonds with other atoms. See, when atoms interact, the core electrons deep inside are protected. They're isolated. It's really only these outer shell electrons, the valence electrons, that we actually have available to play with in our recipe. So knowing an atom's valency tells us exactly how many bonding ingredients it's bringing to the table. Now, the absolute genius of the Lewis diagram system is that it uses simple dots or crosses to represent those valence electrons. We don't have to draw complex 3D clouds or, crazy inner orbital rings. We simply write the chemical symbol of the element to represent the nucleus and inner electrons, and then we just surround it with those dots and crosses. It keeps our chemical ingredients highly visual, distinct, and incredibly easy to track as they move around. And this brilliantly illustrates what our final visual goal looks like. Take hydrogen chloride as a quick preview. Notice how hydrogen's electron is represented by a cross, and chlorine's valence electrons are represented by dots. By placing that dot and cross right next to each other between the letters, we can clearly see a bond has formed. Every single electron is accounted for, and everyone's outer shell is full. That's the exact visual perfection we're aiming for today. Section 2. Ionic bond. Sodium chloride. The transfer. All right, let's put these rules into practice with our very first recipe, everyday table salt. Let's compare our two starting ingredients side by side to see exactly how many dots and crosses we're working with. On one side, we have sodium, a metal, which has an electron configuration ending in an unpaired, lonely, single valence electron. And on the other side, we have chlorine, a nonmetal, bringing 7 valence electrons to the mix. It has 3 pairs and just 1 unpaired electron that is desperately looking for a partner to complete its outer shell of 8. So, here's the cooking method for ionic bonds. It is a complete and total transfer. Because chlorine has a much higher electronegativity, it essentially just pulls that 1 valence electron completely away from the sodium atom. In a Lewis diagram, you'd physically move the dot representing sodium's electron all the way over into the empty space in chlorine's outer shell. So the crucial point is what actually happens after this transfer. Sodium has lost a negative electron, right? So it becomes a positive Na+ ion. Chlorine has gained a negative electron, completing its shell, and becomes a negative Cl- ion. We place square brackets around them in our Lewis diagrams to show that they are now charged ions. And because opposites attract, these positive and negative ions lock together into a massive, stable 3D crystal lattice. That complete transfer is the absolute hallmark of an ionic bond. Section 3. Covalent bond, hydrogen gas, the single share. Now we're going to switch our cooking technique away from transferring and step into the world of sharing. To master covalent bonds, I want you to remember one absolutely vital guiding rule. It's the covalent mantra. You give what you get. Because these nonmetal atoms have really similar abilities to attract electrons, neither side can completely steal one away, so they just have to compromise. If an atom needs 1 electron to be full, it has to offer up one of its own electrons to share in the middle. You give what you get. Let's lay out the starting materials for our simplest covalent recipe. We've got 2 identical hydrogen atoms looking to complete their outer shells. Each hydrogen atom has exactly 1 valence electron, represented by a single dot or cross. But remember, the first energy shell needs 2 electrons to be stable and full. They both need 1 more. As these 2 hydrogen atoms approach each other, some pretty incredible invisible physics takes over. The positive nucleus of one atom starts attracting the negative electron of the other, but simultaneously their 2 positive nuclei are repelling each other. Eventually, they reach a specific sweet spot, a minimum energy distance, where the attractive and repulsive forces just balance out perfectly. They get locked together in a state of stable equilibrium. And that gives us the final result of our single covalent bond, an H2 molecule forms. Think back to our mantra. Each hydrogen needed one electron, so each gave one electron to the middle. We just draw the H symbols next to each other with one dot and one cross securely shared right between them. They gave one, they got one, and now both beautifully experience a full outer shell. Section 4. Covalent bond. Carbon dioxide, the double share. Okay, time to elevate our sharing technique to the next level with a slightly more complex recipe. Let's check our prep station. To build carbon dioxide, we need one central carbon atom, which brings 4 valence electrons to the table. We also need 2 oxygen atoms. Each oxygen brings 6 valence electrons, meaning they each have 2 unpaired electrons just desperately waiting to form a bond. So here's a puzzle for you to chew on. How do we arrange these dots and crosses to make everyone's outer shell full? Carbon has 4 but needs 8. Each oxygen has 6 but needs 8. No one is giving up their electrons entirely, so how do we satisfy everyone's outer shell using only the ingredients we have? Well, the solution is our mantra. You give what you get. Carbon sits in the middle. It needs 4 electrons, so it has to give 4 to the middle. It turns to the oxygen on its left and gives 2 electrons, getting 2 back from oxygen in return. Then it turns to the oxygen on its right, gives its remaining 2 electrons, and gets 2 back. Everyone is giving exactly what they need to get. Now, what's really interesting is how a double bond actually looks visually. If we think about an oxygen molecule, O2, for reference, you wouldn't just have one pair of electrons between the atoms. There are 2 pairs. That's 4 electrons total sitting right between them. When 2 pairs of electrons are shared between the same 2 atoms like that, we call it a double bond, and you can just draw it as 2 parallel straight lines. Applying that back to our carbon dioxide recipe, we get a beautiful, highly symmetrical outcome. Carbon in the center, flanked by double bonds on both sides connecting to the oxygens, a totally linear CO2 molecule. If you count the electrons around any atom in this structure, you'll count exactly 8. By sharing multiple pairs, our mantra successfully filled everyone's outer shell, creating a really stable, linear geometric shape. Section 5. Reviewing the bonds. Mastery achieved. We have successfully followed the recipe book for 3 vastly different molecules. So let's bring this complete picture together and see how this builds. We started with sodium chloride, an ionic bond characterized by the total transfer of electrons to create locked, charged ions. Then we moved into covalent bonds, characterized by electron behavior where atoms actually share to complete their shells. Hydrogen gas showed us a single shared pair, while carbon dioxide pushed us to see how atoms can share multiple pairs to form double bonds. It's the exact same basic rules of valency, just applied in beautifully different ways. You now possess the exact visual tools and rules that chemists use to map out the microscopic universe. You know how to track valence electrons, how to transfer them, and you absolutely know the golden mantra: you give what you get. The entire periodic table is essentially your pantry now. So I leave you with this. Look at a bottle of water or the sugar sitting in your kitchen. Now that you know the rules of the recipe, what molecule do you want to build next? Thank you so much for joining me on The Explainer. Keep learning, and I'll catch you next time.